For this lesson, we're going to introduce the idea of what's known as the inverse of a function. This is something that you've made practical use of already, although you may not have referred to it as an inverse, and there's really no reason why you would have. Let's start with a fundamental definition, which is that an inverse of a relation can be found by interchanging domain and range for that particular relation. Now, if you happen to have points, that can be made much easier to see because it's simply taking the x and y values or the x and y coordinates and swapping them for each point. If we were to represent that exact same situation graphically, what we would find is that it ends up being a reflection. Now, up until this point, you've learned about reflections. You've learned about, in particular, you've learned about reflections in the y-axis or when it comes to parabolas. But we're going to be looking at a different type of reflection here, a reflection in the line y equals x. And I'm going to illustrate that to hopefully make that very clear to you. So in this case, determine the inverse of these 3 points, this set of points. So the inverse is another set. So I'm going to use set notation. It's going to be a set of points. And then for every one of these points, I'm simply going to reverse the x coordinate and the y coordinate. So the point 0, 1 has an inverse at 1, 0. The point 3, 4 has an inverse at 4, 3, or an inverse point. And the point 2, negative 5, the inverse point for that is negative 5, 2. Now, I could plot these on a graph and show them to you, but it wouldn't really demonstrate this idea of a reflection in the line y equals x very well. So I'm actually going to go through a number of graphs and just quickly show you that idea of the reflection with some pre-generated stuff that I've already prepared for you. So here's the first one. So I'm starting with what's in blue here, which is the line y equals 2x plus 3. I used GeoGebra, which is a free graphing software like Desmos, to do this graph. My dotted line here is the line y equals x. So that is the mirror line when you're talking about an inverse. And if I took every point, let's start with the y-intercept. The y-intercept here is at 0, 3. That means that the inverse point to that is at 3, 0. And you can see that that lies on the red line. Another point, let's pick one that's a nice point. Here is the point negative 1, 1. And so if I reverse those x and y coordinates, I end up at 1, negative 1. And you can see that that is also along this red line that I formed. Now, because it's just a linear relation, I can actually determine the slope and the y-intercept, and it turns out that this red line has the equation y equals x minus 3 over 2, or you could write that as 1/2 x minus 3 over 2 if you wanted to put it in slope-intercept form. And that is the inverse to our original 2x plus 3, and hopefully you can start to see the idea of that mirror image. Notice that where the two lines cross each other, that is actually on the line y equals x. So the mirror image of that point is the exact same point. Let's look at a few others to illustrate this. In these cases, I've already put in the first part, which is in blue. And then just to go through that process again, I'm going to pick a few points. So for example, the y-intercept here is at 0, negative 3. So I'm going to find the corresponding point, which is at negative 3, 0. What's another point? Here I have the point 1, negative 2, so I'm going to find negative 2, 1. And I have the point here at negative 1, negative 2, so now I'm going to find negative 2, negative 1. Another point, actually I labeled it here. This is one of our inverse points that I labeled in red, but there's a point from the blue graph there, which is at negative 2, positive 1. And that's going to change into positive 1, negative 2. And there would be another point from here, 2, 1, changes into 1, 2. And that's more than enough for me to be able to try to draw my parabola. Always a challenge with this stylus I use for doing these presentations, but good enough. Some interesting things to note here. This parabola opens up, which is in the positive y direction. The inverse to this parabola opens to the right, which is in the positive x direction. So your direction of opening actually tells you a little bit of information as well. And if you remember it from our discussion about what makes a function, you can see that this inverse, which I've done in red, is not actually a function. The blue parabola is a function. It passes the vertical line test, but the inverse in red does not pass the vertical line test. It is not a function. Now let's continue with that general shape. My next example is the radical function. And in this case, I have a radical function that's just been shifted over a little bit, but it's the square root of x minus 2. That looks very much like that inverse that we just found. This is like a parabola lying on its side. But notice I only have half of the parabola, the top half of the parabola, and this is a function. It passes the vertical line test. If I take some of the points, for example, 2, 0 moves to -2 when we take the inverse. 3, 1 has an inverse point at 1, 3. Let's find another point, 6, 2, 2, 6. And that's enough for me to try to draw that. And if I had done a better job, it would have been clearer. But now what we actually have is something that looks like a parabola. But in this case, I only had on the original, I only had the values going in the positive y direction. And notice the branch on the parabola, or the part of the parabola that I've drawn, only has values that are going in the positive x direction. So when we swap the x and y coordinates, we also swap all of the corresponding properties that go with the y direction and the x direction. So in this case, the original always grew in the positive y direction, and so the inverse always grows into the positive x direction. So you can make use of that knowledge when you're doing things like this. And then I think I've got a final example. I guess I want to also highlight that reflection, that line y equals x. And then I've got a final example here. If we take a look, same idea, another parabola. I'm just going to do this one quickly. 2, -3 ends up at -3, +2. What's another good point on here? Do I have any more good points? Yes. 4, -5 ends up at -5, 4. Unfortunately, I didn't choose my scale as carefully as I should have. And what's another good point? 0, -5 ends up at -5, 0. So right there. And this parabola, still enough points there for me to do a reasonable sketch of it. And we end up with something like that. And the last time, just to emphasize this, this one is opening in the negative y direction. And so it should not be a surprise that this one is opening in the negative x direction, because of the x and y's have swapped in all ways. Okay, let's move on to the note proper itself. Actually, we already did start the note. So we just talked about inverses, but now I want to talk about a subset of inverses, which are known as inverse functions. So in the examples that I just did, I showed you that you can start with a function and end with a function, or you can start with a function and end up with an inverse that is not a function. Here we started with a function and the inverse is also a function. Here we started with a function, but the inverse is not a function. So if you start with a function which has a special set of rules to go along with it, basically saying that for every input of x, there's a single, consistent, predictable output of y. For an inverse function, that means that when you take the inverse itself is also a function, also satisfies those same rules. If it turns out that your inverse is also a function, we actually use this special notation to denote the inverse function. I'm just putting in this extra caveat, this extra warning, the -1 here in the function notation. Just in the same way that you had to learn that with function notation, these brackets did not mean multiplication. The same thing is true with the inverse function notation. This -1 is not an exponent. It stands for an inverse. You're actually already familiar with this. You might have made the connection already, which is you learned about, for example, a trigonometric function called sine. You would have learned about that in grade 10. But you also learned about the inverse sine, which had this -1 notation as well. Well, it turns out sine is a function, just it's a very specific form. F of x we normally use as a general function. Sine of x is a very specific trigonometric function. And you can also have the inverse to sine, which is sine inverse of x. So you're already familiar with this notation. So now we're looking at, I just want to reinforce that, but if it's on a variable, x to the -1, of course, that means 1 over x. So that's also something to keep in mind. So let's take a look at the algebraic process for finding an inverse. So algebraically, when we did points, we swapped the x and y coordinates. So the general procedure for algebra is to swap the x and y variables and then rearrange it so that it says y equals. So rearrange your new equation for y. Now, sometimes this gets glossed over when people are talking about it, and then students run into certain situations where they're confused and they feel like they've made a mistake. This process where you swap the x and y variables, it's only applicable if they're generic variables. So if x is the generic independent variable and y is the generic dependent variable, then you swap the variables and rearrange. Sometimes, though, we write equations or functions where the letters that we use have very specific meaning. H for height, T for time, V for volume. Under those circumstances, do not swap the variables. You're just going to rearrange the equation. Because those variables, those variable names, they have a specific meaning, and if you swap them, it doesn't make sense anymore. If t is time, then t always has to represent time in whatever relation you're working on. And a final note, if your equation is in function notation, change it over to what we call xy notation, where you just use variables. If you're using a generic function, f of x, g of x, h of x, you probably can make your first change is just to replace that with a y. So now I've switched from function notation to xy notation, and I'm going to find the inverse of this and determine whether or not it's a function. So what I'm going to do now is I'm going to swap my x and y because this is generic. This is the dependent variable and x is the independent variable. So I'm going to rewrite that as x equals 4y plus 3. Now I'm going to isolate the y. So I'm going to bring the 3 over to the left side, and I end up with 4y equals x minus 3. And I divide both sides by 4, and I end up with x minus 3 over 4, which you might choose to write in slope-intercept form, just to make it a little bit more familiar, 1/4 x minus 3/4. And the fact that I can write that in the form y equals mx plus b, well, that tells me that this is the equation of a straight line. It has a y-intercept at -3/4, and it has a positive slope, but a fairly shallow slope, so it's going to look something like that. Is that a function? Yes, that passes the vertical line test. And so this is a function because of the vertical line test. And that means I can actually write this using function notation, which is that f inverse of x is equal to 1/4 x minus 3/4. And this letter f has to match whatever this letter was. So if this was g of x in the original function, then this inverse would be called g inverse of x. Now, here's an interesting property. This whole swapping back and forth of the x and y coordinates, or of the independent and dependent variable. It turns out that a function and its inverse perform this very special operation, which is they undo each other. So what that's saying is if you put a value into the original function and get an answer and evaluate that, and then you take that answer and you plug it into the inverse function, it's going to bring you right back to where you started. So that's an interesting property, and I've illustrated that in the most general way here. If I take an input of A into my original function, B is my output. If I then take that B value as my input to the inverse, then I'm going to end up right back where I started with A. So just to illustrate that, take a look at x equals 5. I'm going to start by evaluating what is f of 5, and that's 4 times 5. Wherever I saw an x, I replaced it with 5, plus 3, and 4 times 5 is 20, plus 3 is 23. Now, what is f inverse of 23? I take the result of my original function, and I put that into the inverse, which is x minus 3 over 4. That's 23 minus 3 over 4. 23 minus 3 is 20, divided by 4 is, of course, equal to 5. A function and its inverse function undo each other. F of 2.5, just to show it's not a fluke, 4 times 2.5 plus 3, and that's equal to 10 plus 3 is 13. And then f inverse of 13 is equal to 13 minus 3 all divided by 4. That's 10 divided by 4 is 2.5. Another way that you've experienced the idea of inverses is when you do simple arithmetic. If you add something, what's the inverse? What is the reverse operation to adding? It's subtraction. If you multiply something, what is the reverse or inverse operation to multiplication? It's division. This is just taking that idea of reversing a particular type of operation and just taking it to the next level. And that's it for this introduction to inverses. We're going to look at inverses in more detail throughout the course as it applies to different functions and some of the other things you can do with them. But that's your introduction for now, and there is some of the assigned work from our current textbook.